happy to answer any questions you might have. Yes?
My question was, so gravitational waves only occur when they collide, so like a single black hole just doesn't speed gravitational.
Oh, that's a really great question. So, and that's right, a black hole sitting there by itself doesn't shine gravitational waves. So this new idea of black holes, of trying to see black holes interacting, you need two of them. It's not just black holes that make gravitational waves. If I wave my hands around like this, that makes gravitational waves too, but they're far, far too weak for us to ever have a hope of detecting it. Basically, you either need two objects, or you need the black hole to be ringing in some complicated way. Like when two black holes merge and there's a new but strangely shaped one, that single black hole can send out gravitational waves, but they die away, just like the sound from a bell dies away. It's really an interesting question. Does anybody have any other questions about black holes or space and time or anything like that? Yeah.
So how does the discovery of these gravitational waves lend to the combined sort of theory of quantum mechanics and then the relativity theory and stuff like
That's
that?
a really great question. The question is, how do gravitational waves tell us about how...
Well, then I had like a second part of that. So the front of these waves, when you experience them, or when it sort of hits wherever we're measuring them, what kind of force would that appear to be like, or are we considering gravity to be assigned a charge, like a pull and a push?
That's another really great question. So one question is, what kind of force do gravitational waves exert, and is gravity pushing or pulling? And another question is, how does this mesh together with quantum mechanics and general relativity? So let me tackle the first question first. So quantum mechanics is the theory that describes how things move when how things behave when things are really small. And there is quantum mechanics that you have to understand in order to know how these gravitational wave antennas work, in order to be able to account for how the mirrors are moving. And in fact, quantum mechanical effects limit how sensitive the antennas are. That's part of one kind of the noise, and especially high frequencies, that makes it hard to hear gravitational waves because there's quantum mechanical ringing that we can't get rid of. So quantum mechanics is the theory of stuff that's really small. General relativity is our theory of gravity, and they don't fit well together. The kinds of gravitational waves that we're going to see from space, from colliding black holes and things like that, are not really going to tell us much about how things behave when they're really small. These black holes are small for how massive they are, but they're still sort of city-sized. They're not like microscopic. They're not like proton-sized. There are some things we can learn about quantum mechanics from these experiments, but it's mostly from learning about how the mirrors are behaving and not so much from the gravitational waves directly.
So when you encounter a wave, does that not apply to the, because we didn't originally think of gravity as a wave like that, or it could appear in a wave like that, does that not lend to the fact that it could be in a wave-particle duality and then could be applied to quantum mechanics?
So it could, but probably not in a way that the experiment will be sensitive enough to detect. There are future experiments that might be more sensitive, where you could try to see that, but we don't think these antennas are going to be quiet enough to be able to tell the difference. You can put the detector in different configurations or modes, and if you try to put it in a mode that makes it easy to tell quantum mechanical effects, that makes it harder to hear the gravitational waves and vice versa. So we're planning to tune them so that we can hear the waves from space, but that will make it harder to hear the quantum mechanical effects. But if you tune it a different way, then what you could do is you could actually see these 40-kilogram masses, which are macroscopic masses, and these antennas are sensitive enough that you could see some quantum mechanical effects. But actually mixing quantum mechanics and gravity, this experiment probably isn't going to be sensitive enough to help us. Now, the other thing you asked about was, does gravity have a charge? When you think of gravity in terms of forces, then gravity all masses have the same charge. They're all positive, and in gravity, the masses always attract each other. In electricity, you can have positive charges that will repel each other, but a positive and a negative charge will attract each other. But in gravity, it's always attractive.
So looking at, if you have this wave shape and you're looking at that sort of effect, we're not looking at like a sort of pulling force and then opposite sort of thing?
Yeah, that's right. You can't really understand the gravitational wave in terms of a force, because Newton's law of gravity, which sees gravity as forces between two objects, doesn't include gravitational waves. You need Einstein's theory of space and time being curved. So the real way to think of it is as space and time being curved in such a way that the particles move in the way that I showed. But you can't really translate that into a force. If you try to use Newton's laws, they just won't behave that way. Yes?
You mentioned Interstellar.
Yes.
And the real theories that were applied in that movie. Where should the line be drawn between science fiction and reality?
That's a wonderful question. Where should the line be drawn between science fiction and reality? Well, I'm glad you asked that. I happen to have another slide. So, for a little while longer, this is still the future. So, this was a movie about time travel in a completely unrealistic way. Was it a fun movie? I mean, I laughed. I enjoyed it. I think storytelling is important, and I'll forgive a lot if the story's good, is probably my personal answer. I enjoy movies where they try to get the science really, really right. They didn't here. Like, they knew when they made the movie we weren't going to have flying cars in 2015. I mean, if you've driven on the freeways when it rains, imagine doing that in the air. I mean, it's probably a bad idea. And they knew that. They were just trying to tell a good story. But you can imagine, I'm going to skip ahead a couple more slides here. You can imagine trying to do something more realistic. And that's what they tried to do in Interstellar. So they imagined, what if we went to another far across the universe through something called a wormhole, where space and time are curved in such a way that you can get there pretty quickly. We're almost certain that they're impossible, but not quite. And so since we're not completely sure with science that they're impossible, the story is saying, okay, suppose it is possible according to all the known laws of physics. So nothing that we know to be false is in the movie. It's just a couple of really minor exceptions. Then they went to some place with a big black hole. And this is the most realistic description of what a black hole would look like. They actually ran a computer simulation of what it would look like if you had a disk of matter falling into a black hole. Here's sort of the inner edge of what you see, and then the horizon is inside there. That's the place where you're not coming back. So this was made by solving equations, seeing how the light would move in a more, basically they had bigger computers than what we have at Cal State Fullerton. That's the kind of pictures what I showed you that Haroon was making of two black holes bending the light around each other. And then of course they put a planet next to it, because there's got to be a planet for the story. But this was kind of cool. Suppose I slice through the equator and show you what this black hole looks like. This black hole's funnel looks like this. There's a planet down here. The spaceship sits out here, and their time is flowing basically the same as Earth's. But the time gets curved so much that the ship, they sent a little shuttle down and spent a couple of hours down here, and then it turned out that after a couple of hours down here, like each hour was 7 years back on Earth. Now, I derived those equations. I mean, I wasn't the first to do it, but I just taught them in classes, and I talked about them in talks. But I never really felt it the way I felt it when I watched the movie. It's so sad that he's watching his daughter grow up before his eyes. And, you know, that's what a story can do for you. So it's fun when they try to get the science right. When the science is egregiously wrong, like this movie called The Core, melted the Golden Gate Bridge by boiling the water under it. I mean, you know, okay, metal doesn't melt when you put it in boiling water. That's how we have pots. Okay, but they screwed that up. And so that's irritating maybe if it's egregious, but I'll forgive a lot if the story is good. The main reason The Core bugged me was the story was bad. So maybe that's a long-winded answer, but
6 hours long.
6 hours long.
It's way too long.
Okay. But anyway, I'm opinionated about it. I love good movies with good stories, and if they have good science, that makes them even more fun. Does anybody have any other questions about stuff? I skipped through a bit of the time travel stuff, but questions about black holes and traveling in time, I can answer a couple more questions. Yes?
How do colliding black holes behave in strong magnetic fields?
Oh, that's a great question. How do they behave in strong magnetic fields? So two black holes by themselves wouldn't really have any electrical or magnetic charges, because random electrical charges in the universe would be attracted to them and fall inside and cancel it out. But if you have two black holes that have a disk of matter around it, and suppose you have two black holes like this meet each other, that matter gets magnetized. And how does it change with magnetic fields? Well, it turns out what the magnetic fields can do, and this is way too much for me to be able to explain in all the mathematical detail, but what they do is they can cause some of the matter that's falling in to not go into the black hole, but to shoot out in little jets on the ends. And recently, just this year, was the first computer simulation. It was from a group at the University of Illinois that actually showed this effect. And so you can get these giant jets of matter shooting really rapidly away from the black holes. And this is something that we hope to be able to see, because the matter shooting away is a really bright signal we can see with ordinary telescopes. And if we could combine that with the gravitational wave measurements, we could learn more about the black holes than from either one by themselves. So they can actually have very dramatic effects on the matter. This is how they think these objects called quasars work. As the matter falls in, the magnetic fields cause the matter to shoot and to accelerate upward. So that's part of how things like that can work. So that's a really interesting question. And the short answer is it's complicated. Any other questions? Yes?
Do you think it ever be possible to have a black hole separate?
That's a wonderful question. Could a black hole split?
Or is black hole pretty much like all of matter?
That is a wonderful question. So they kind of are. A black hole cannot split. It's the same reason that if I had a glass and I dropped it on the floor and it shattered, and you watched a video of it, you could tell this looks right, it's falling and shattered. But if you rewind it and the glass all comes back together, that looks totally fake. It's because the amount of disorder, it's called entropy, is actually going up. It turns out the surface area of a black hole is related to entropy. And so when black holes merge, the surface area goes up. If you cut them in half, you actually decrease the total amount of entropy in the black hole. So that's actually not possible. So stuff can fall in, but stuff can't get out, and you can't split it in two. Running a black hole merger back in time is the same as watching the glass coming back together. Yes?
But what about if it turns out that the second you see that it could self-destruct?
Yes, and that's a good question. So there's a conjecture that isn't proven yet. The black holes can only spin less than, like 100, it's a less than, not a less than or equal to. So they can spin at 99.999% like this, but not 100%. As long as it's less than that, then you can never split them apart. If it's more than this, so there's no horizon, then there's no reason that what's going on inside can't affect the outside world, and maybe they could come apart again in some complicated way. You couldn't completely rule that out. But for the ordinary black holes that actually have horizons, it's not going to happen. If we're exactly at 100%, then all bets are off. So that's another really interesting question. Any other questions? All right, well, I'll stick around afterwards if anything, if there's anything else you want to chat about on the way out, but thank you again very much for coming.
So I just want to say really quickly how incredibly fortunate we are to have the support from Dr. Lovelace, I'll say Fullerton, the STEM Squared program. We really do appreciate it. The talks will continue on Wednesday when Dr. Joshua Smith will be here to continue. If you didn't get a chance to sign in on the way in, please make sure you sign in on the way out. Thank you again.
You asked this question, he's like, please ask this question for me. I was like, go for it. No, you pulled it out. Sounded like you didn't. Well, I don't have internet. I know more of the
But basically there's a North Pole and a South Pole. And so there will be jets shooting up either way. And sometimes they can be like light years long, because once you leave the black hole, the matter just keeps going.
Yeah.
So until it runs out of...
Yeah. Well, it won't run out. If there's no friction, it just keeps going. And
Well, at the
sometimes-
source, would you eventually run out of...
Oh yeah, you might eventually run out of matter, but like the matter that gets shut out just moves.
Keeps going.
Right.
And eventually it disperses to where we can't see it anymore, but you can see these jets, like little water jets of gas that's
I
going
want
for
to
like
say,
light years long.
there was a black hole in Star Trek
Yes.
that was having this similar...
Yeah, so that's roughly right, but the red goo that made the black holes, that's all done. So, and also going through a black hole and coming out someplace else is fake. You need a different kind of curved space-time, a wormhole to do that.
That was last year's talk.
That's right. That was last year's talk.
Yeah.
Yes.
I have a question, just in regards to the whole, because I was just curious, the time travel aspect and how time relates to gravity. If you took gravity out of the equation, is there still time, or is that directly tied to
Yes, there
gravity?
is. And in fact, this was another slide I didn't have a chance to get to. Time travel going into the future just means you experience less time on the way than everyone else. And you can do that even without gravity by moving really fast. So an example I actually give my students on an exam in my class is I have an identical twin brother. And he's 13 minutes older than me, but if I put him on a rocket that accelerated away from the Earth at just ordinary, comfortable Earth gravity acceleration, so it feels just like this, and he goes out and then comes back, and it takes about 30 years or so. By the time he got back, he'd be the same age, because his clock would be ticking a little bit slow. And if he went much closer to the speed of light, or traveled longer accelerating at one Earth's gravity, then when he got back, he might be millions or billions of years into the future. So future time travel is possible. And not only that, we've put an atomic clock on a plane, and I talked about this in last year's talk, and we flew it around, and then when it got back, it was a few billionths of a second in the future. But backwards time travel requires something like a wormhole, and it's probably impossible.
Okay, yeah.
Yeah, but that's a great question.
Check our YouTube channel and check for last year's video. Just like a hot link. For questions about time travel, click here.
Yeah.